Hello and welcome to this presentation on the magnetism of the first row transition metal complexes. There are three main types of magnetisms for these first row transition metals. First is paramagnetic, second is ferromagnetic, and the third is anti-ferromagnetic. They all have different properties. A good example of this is the magnetic moment versus temperature. As can be seen here, each different property behaves differently at temperatures. We'll first quickly summarise paramagnetic compounds. Paramagnetic compounds are made up of unpaired electrons. These electrons are separated particles. As be seen here by the arrows that are, in relative terms, widely separated with all in random directions. Seen by the magnetic moment versus temperature graph, a paramagnetic complex has an almost linear graph to it. It shows how the magnetic moment and temperature for a paramagnetic compound is near linear. I'll quickly summarise ferromagnetic compounds. These compounds have aligned dipoles and are closely packed together. As can be seen by the arrows in the diagram, where, as demonstrated by the arrowheads, they're all pointed the same way to show the dipoles are aligned. Also, a lot more of these fit into the same space than there was for paramagnetic. You can see here by the graph, at lower temperatures, ferromagnetic compounds are have a much greater magneticity about them. However, as this increases, there is a point known as the Curie point, where the magneticity sharply switches to a more known graph that looks more like the paramagnetic graph. These compounds are often iron, cobalt, and nickel. And lastly, to quickly summarise anti-ferromagnetic materials. This is where the dipoles are aligned oppositely. As we see in this diagram, and demonstrated by the arrowheads, each arrowhead alternates between the direction it's pointing. This shows how the dipoles are alternating 180 degrees to each other. These are, once again, very tightly close packed particles, as can be seen by the amount fit in a similar space to paramagnetic. On the temperature graph, as we can see, at lower temperatures, anti-ferromagnetic compounds are the exact opposite of ferromagnetic compounds, where at low temperatures, the magneticity is much lower. However, when it comes to these compounds, there is a point called the nil point. It takes a sharp detour and becomes much more like a paramagnetic. It shows that roughly at a temperature, all magnetic compounds become very similar in the way they react. Now we will talk magnetically about spin-only compounds. Here, the shape of the complex changes. Common compounds that use these are the shape are chromium, nickel, and high spin and low spin compounds can also change the mu of the complex. High spin and low spin can also change the mu of the complex. In this regard, mu stands for magnetic moment. So here we can see that mu of spin only is equal to the square root of n, which is number of unpaired electrons, open bracket, n plus 2 close bracket, times by mu b. Mu b can also be known as the Bohr magneton, which is equal to EH over 4 pi me. Here is a quick table to demonstrate how the magnetic moment changes depending on the compound's spin shape. Low spin compounds have not been included here because they have a magnetic moment of 0 as there are no unpaired electrons. A high spin D6 complex, as you've seen by this by the equation, with the numbers correctly substituted in, have a magnetic moment of 4.89 times the Bohr constant. A tetrahedral D8 complex will have a magnetic moment of 2 open bracket 2 plus 2 close bracket square rooted times, once again, the Bohr constant, which is equal to 2.83 times Bohr constant. We can also talk about mu F. Here, F stands for the effective magnetic moment. There are 3 equations working this out, but we are only going to focus on one because it is the most important equation. here we can see mu f is equal to the square root of 4s open bracket s plus 1. Now the difference between n and s is that in this table I've put together a series of ions, metal ions that is, their configuration, their calculated UF, and their observed UF. Just looking at the top row first, we've got titanium 3+. Configuration is D1, which means there is only one electron in the 3D subshell. Using the previous equation, it can be calculated that it has a magnetic moment of 1.73, and when this was observed practically in a lab, it was always observed between 1.7 and 1.8. So the calculated value sits nicely in the observed value. As we see here, that trend continues down for the most part, where the calculated value usually sits quite nicely within the observed value. Manganese 2+ or iron 3+ have the greatest magnetic moment, as can be seen in this table. Now, to summarise, we've talked about how the temperature affects the magnetic moment, and also how the type of magnet affects the, and also how the properties of the magnet affect the magnetic moment at different temperatures. And look at how different ions from the first row transition metals and the different configurations all have very different magnetic moments. And we've also seen how the actual structure and the spin of said moments affects the magnetic moment.